Welcome back. Okay, so we're looking at the general formula for doubling and half-life periods. So remember, this is just for doubling and half-life. We don't have to go up by 2s. We could go up by 3s, 4s, 5s, or 6s, 7s, 8s, 9s, so on and so on. But it wouldn't be called doubling, right? And half-life, we certainly don't have to always go down by a half. We could go down by a third, a quarter, a fifth, a seventh, but it certainly wouldn't be called half-life. So in the general case, it would just be exponential growth, and the other one would be exponential decay. But when we have the bases that are simply 2 and 1/2, we can give them the special names, doubling time and half-life time. So these are formulas, okay? And these are standard letters that we use across the sciences to represent these formulas. So this is a number, okay? N of t. So this is function notation. So this is going to talk about where n of t is the number of bacteria. That's how they used n, okay? So it just means number of bacteria after t hours. So our variable is t, okay? So this is function notation. We call the function n for number, and it's going to be with the variable t. C is the number of bacteria at the beginning. It's what we call the initial number that you start with. D is going to be the doubling period, and T is going to be the amount of time for the quantity to double. So it's this idea of having a doubling time and the question giving you a certain amount of time, and you have to figure out how many doubling periods that is. We saw that in the last example we did. So here we have M of T is going to be the number of bacteria present. I don't think so. M of T is going to be the mass of substance present after T hours. C will be the initial mass, okay? And H will be the half-life period. The amount of time required for a given quantity to decay to half its life. Okay, so same idea. So let's look at this example. A biologist, he starts with a sample of 2,500 bacterium in a culture and finds that he puts in a culture and finds that it doubles. Maybe we put the word it there. I did not type these. That it doubles every 3 hours. Okay, so let's get a formula here. These are the formulas that we need. We've developed general case formulas. Let's look at which one we're going to use here. It has doubling every 3 hours. So it looks like that this is doubling time. So the general case formula will be the number of bacteria is going to be the initial amount times the doubling time, or T over D. Now we know some of these numbers. They say this is why we have the doubling time, because it's 2, okay? And the doubling time, D equals 3 hours. So it takes 3 hours for it to double. The initial amount of time that they're giving us, the total amount of time, is 10 hours, okay? So it's going to double every 3 hours, and it's allowed to go for 10 hours. And our initial amount was 2,500. So we can do this. N of 10 hours is going to be 2,500 to 10 over 3. Oh, you can't see what I'm doing. There you go. And what that's going to change to is I'm going to take that 10 divided by 3, and it gives me 0.333333. And so that is the number of doubling times that are going to go by. So in 10 hours, there's going to be 3.3 doubling times go by. So what I do is now I can do all of this on the calculator, and you know what? I probably will. Instead of doing this, let's get rid of that, because what's going to happen is I'm going to have an estimate, and if I only estimate one, it's going to be great. So here's my calculator. So what I want to do is 2 to the exponent, and I'm going to do 0.33333. Oh, no, not 0.3333. It's going to be 2 to the exponent 3.33333, and I'm going to fill that up. I'm going to hit equals, and then what I'm going to do is I'm going to take that and times it by 2,500, and I'm going to get approximately, and that's what that symbol means, approximately, that little dot above it, 25198.42. Now, let's think for a minute. First of all, I need to do a shout out to Ashley there and say that I had to write over top of some white out there. It wasn't fun at all. Okay, next thing I have to tell you is I really have a hard time understanding what 0.4 of a bacterium is. It doesn't work. So we're either going to have to take that and round up or round down. My personal point of view is, yeah, I'm only going to take the whole number. So even if this was 0.9, if I'm talking about the number of bacteria there, I would kind of say, well, it's not a full bacteria. It doesn't pop into life until it's a full bacteria. So I would be rounding down in that case anyway. But we'll talk more about that as we do more examples. So what happens is, what we've got is this 2,500. Now, if we think about it, logically, it's going to double 3.3 times. So it should be 2,500, double it once, double that again, double that again, and then 0.333 a little bit. So, and that makes sense, okay? So it's working out. How long will it take for the sample to grow to 640,000? That's a great question. Let's take a look at that. So our formula is the same that we had before. The only difference is we don't know the time in this one. You see what's going on? We know the initial amount. You're starting off with the same amount. You know that it's still doubling time. And it hasn't, the material hasn't changed. It still has a doubling time of 3 years. The question is, how long is it going to take until the total number that we have is 64,000? That's kind of a cool question. So we'll set that up. You'll have 64,000 equals 2,500 to t over 3. Now that's pretty scary. You've never seen something like that. Oh wait, yes you did. You've been working on exponential equations. You worked on exponential equations in the last lesson. So if we look at this, our ideal is to isolate t. You want to isolate. That's what we want to solve for. So I need to get t by itself. But that t is up in the exponent. So I'm going to have to do some work. So I need to get it down. How do we solve exponential equations? Because that's what this is. This is an exponential equation. And the way we solve exponential equations is by knowing that if a equals x, a to the x equals a to the y, then x equals y. That's what we have to do. We got to get it down to have the same base, and then we can equate the exponents. Interesting. So let's try this. First thing I want to do is get rid of the 2,500. What is it doing to the 2? It's multiplying. So the inverse operation would be to divide. So my first step is going to be to 6,400 divided by 2,500 is going to equal 2 to the t over 3. So I still have that exponent way up there. So 604,000, sorry, divided by 2,500 is going to be 256. Okay. Now 256 and this they're not the same. But if I could get the bases the same, then I'm laughing. So let's try, because that's what I want, right? So I want to get bases the same. That's what I want to do right here. Maybe I should put a little bracket around this so that we don't get confused. So we want to get the bases the same. Well, I'm wondering if I can change 256 to the base 2. 256 to the 4 is 16, too small. 2 to the 5, 32. Okay, I'm going to go high. 2 to the 7, 128. Not bad. 2 to the, let's try 11. Too high. 2 to the 9, 512. Hey, I'm close. 2 to the 8, 256. I got it. And I got it by guess and check. Okay, I went through and tried to find it. So it's 2 to the 8. Look, my calculator still says it. Equals 2 to the t over 3. So now we know that the bases are the same. And we have an equality here. So therefore, 8 equals t over 3. Let's keep in mind what we're trying to do here. We're trying to find out t. So I'm going to multiply both sides by 3. And you're going to get t equals 8 times 8 times 8. So 3, not 8 times 8, sorry. 3 times 8, which is 24. So that means that we're going to need that the population will grow to 640,000 after 24 years. So how many doubling times are going to happen within those 24 years? Well, what you do is you take the 24 and you realize that it takes 3 years for it to double. So it's going to take 8 years. And notice that that's here. Now there's reasons for that, but we can always work backwards and come up with that. So that's page 131. Let's see what's over. We've got page 132 to do next, and I think I'll stop the video and do that one on a separate video.